Great, yeah, I think we'll get started as we wait for a few more people to join online. But yeah, thank you for joining us today. We have our very own Zhuang today speaking to us about SEPs, so solar energetic particles. Bin was at the University of Science and Technology in China until 2019, so that's when he graduated with his PhD. And since then, he's been working with our CME group at UNH with Professor Nelly Legaz, focusing on coronal mass ejections and SEPs. So whenever you're ready, Vin,
yeah, I'm ready.
Take it away.
Okay, cool. Thanks, Emma. And thanks everyone for this opportunity. And I guess maybe not. Some of you might have known me before as I joined UNH in 2019. And I have been working with NOI for more than 3 years now. And today, though, as you see, the title is majorly talking about SEPs. So this is like a brief summary of what we have been doing since I joined UNH, and it will include some time stories related to the understanding the acceleration and the release of solar energetic particles. But we focus more on using observations from multiple viewpoints and in multiple wavelengths. So let's see first, what is solar energetic particles? SEPs, or just the SEPs hereafter, they're from superthermal to relativistic energies, and they are thought to be accelerated near the sun. And traditionally, they are categorized into 2 groups. One is impulsive event, means that you have a very quick onset and a very short duration of the SEP event. And one is the gradual event, means that your SEP will gradually enhance and then gradually decay. And as for the impulsive SEP event, they are thought to be related with magnetic reconnection processes during solar flares. And as for gradual SEP events, they are thought to be driven by shocks associated with wide and fast coronal mass ejections. And here, I would like to introduce one more definition, which is the large. The large means that the ion intensity in the energy range above 10 MeV exceeds 10 PFU. So the large and the gradual SEP event is one of the most interesting or hard aspects in the space science and the space weather studies, because it includes many complicated physics mechanisms and it has strong space weather effects. And here I will show you one movie. It's the CM eruptions. And you can see there are some noise stones on the CCDs caused by the accelerated particles hitting the telescope CCD. And this is the in situ part. It's observed potent enhancements associated with the solar eruptions, and then from the energy of few MeV to even 5 MeV. And this is a quite large event, and this is a famous event. In 2003, we call this like Halloween event. And studying SEP is not only because it's complicated physical mechanism, but also, as I mentioned, it's space weather effect or space. And as you might know, we need to, when we study an object, we need to know how they will, sometimes we need to know how they will influence us. And as for SEPs, of course, it will influence human high technology instruments and like the satellites, like our electronic power grids. And of course, it will also bring radiation exposure to astronauts. Even now, we will have more astronauts into the space. And with all of these importances, and to have a further or deep understanding of SEPs, we need to study its acceleration, release, and the transport of SEPs, because you need to know how they are generated and how they propagate or transport from the acceleration region to the in situ part we observe it. And let me spend one more page to talk about observations. Since we need to know many things, we need to study the SEPs. One direct way is that we use observations, and especially for observation from multiple viewpoints. This is 3 images. There are 3 images show you how important of the observation from multiple viewpoints can be used to study the SEP distribution in the heliosphere. And distribution can be, and these multiple viewpoints observation and distribution effects can be further used to indicate or study the SEP acceleration and transport effect. And then we have like the observations, not multiple observations from not exact, but from late 20th century into the stereo era. And today we have like even more like Parker solar probe and the solar orbiter moving much closer to the sun. And that with all of this information, we could know more or know deeply about SEPs. And this is one more image showing the locations of some spacecraft, not today, but recently. We have stereo A and the spacecraft at one point. Unfortunately, we lost stereo B today. And then we have Parker solar probe, we have solar orbiter moving much closer to the sun. We have some planetary missions like the Backclomb or Maven or Juno, yeah, maybe. And this is a figure used to indicate like spacecraft or observations in multiple viewpoints distributed in the heliosphere. And on the right, we can see some observations in multiple wavelengths. This means that when you study SEPs, you need to study its associated eruption phenomenon. And the in situ observation is not enough. You need to rely on some multi-wavelengths observations from for example, from the EUV wavelengths to the radio and even to the white light coronagraphs that you can study the CMEs, you can study type 2, type 3 radio bursts, you can study the EUV wave and the solar flares. And with all of these observation or information today, we are going to talk about our studies. And I need to start from a specific point because talking about observations is too broad. So our stories start from these tiny points that the relationship between the SEPs and the CMEs. As you have known that SEPs are accelerated by shocks and the shocks are driven by CMEs. So you might expect a relationship between the CME and the SEP. So based on this scenario, there are many statistics focusing on studying the CME properties like the speed, the angular width, or the kinetic energy, and with the SEP intensity. And you can find some results here. But you may notice that, for example, let me show you. For example, this one, the kinetic energy or the speed, the data points are quite scattered. So it means that there is not a pure relationship or correlation between the same property and the SEP peak intensity. And there may be many reasons in causing such a scattering or scattered data point. It could include the inner physical mechanisms like acceleration and transport effect, and it can be influenced by the magnetic connectivity between the SEP source region and the observer. And also it can include other factors like the background medium, solar flares, incorporation, and the seed particle populations, which the shock acts or the seed particle population. And in the following part, I would like to use these seed particle populations as a key role to link our studies together. But I will not talk about this seed, but just to use it as a linkage. So the following stories will contain 3.5 parts. 3 have been published and 1 is still in preparation. And the first 3 parts will be talking about seed particles and the twin CME scenario. And then the final part is like a bonus. That's what we can use these multiple space observations to study the SEPs and SEP associated phenomena. Let's direct go to the first story. The first story is about the twin CME SEP event in solar cycle 24. We record the previous the scattered data points of the CME's property or CME speed and SEP peak relationship. And we know that some factors would influence this scattering. And a scenario called the twin CME scenario was proposed to try to explain why the data points are quite scattered. So in that scenario, it includes a fast primary CME and associated with one or more preceding CMEs. So it means that you have one preceding CME and you have one primary CME, and this primary CME will accelerate those particles, while the preceding CME could play some roles in, like I will introduce later. And in this twin CME scenario was found to be more favorable to the SEP to the particle acceleration and to enhance the SEP peak intensity. And the role of preceding CME here is that they can provide enhanced seed particle populations or the turbulence or higher turbulence level. And some some people, based on this scenario, some people tried to use this twin CME to explain the scattered data points, the CME SEP data point in solar cycle 23, and they say that okay, the twin CME scenario can be quite reasonable to explain why that's scattered, but there may exist some questions that I will introduce now. Before our questions, I would like to mention two things. In the twin CME scenario, we have to. The first is that it requires the two CMEs have some special overlapping. For example, if one CME propagates in this way and one CME propagates this way, so they are totally unrelated. So we will require some special overlapping. But in the same time, it doesn't require the two CMEs will directly interact. It just requires a specific time interval between the two CMEs, for example, 12 hours or 10 hours. So what questions come here? With the statistics in solar cycle 23, we only have single viewpoint observations for the CMEs. That means that when you observe CMEs, what you are seeing is just in the projection plan. So you don't know, for example, two CMEs, you don't know whether they will overlap in the real 3D space because what you observe is just in the plan. So you don't have the 3D information. So that's our first question comes, whether the CMEs, the twin CME events have the CMEs in the twin CME events will have special overlap in 3D space. And the second and the third question is related to the time interval and the CME interaction type. You know that there's only a time interval requirements for the twin CME scenario, so it doesn't require meaningful or direct CME interaction. So we don't know does the interaction of successive CMEs play a role in large SEP events, and due to the different speed of the two CMEs and the time interval, the CME interaction will have different types. For example, the ejector-ejector interaction or the shock-shock interaction. So we don't know whether different types of CME interaction would influence the following SEP peak intensity. That we are trying to answer these three questions. So let's see our first point. Now we have assumed that we have only one, or we have only single viewpoint observation from the Earth. That's what they are doing in solar cycle 23. So you see two CMEs here, and with this image, with this figure, you might say, okay, these two they might overlap with each other, and they might be in the twin CME scenario. But is it true if we combine two more viewpoints from still B and still A? And let me show the result. The answer is no. The two CMEs are propagating along totally different direction, and there, of course, there's no CME interaction. And this is only one case. And to do so, we just to study how these multiple viewpoints observation could influence our SEP detection. We study all the twin CME SEP ridge events in solar cycle 24. Well, solar cycle 24 because in that solar cycle we have stereo A and we have stereo B. So that we have multiple viewpoints observations, and we identify the twin CME SEP ridge events based on these criteria. And I don't need to we don't need to go to the details. But let me mention one more thing. On the right is that with multiple viewpoint observations, it doesn't mean that it means that you can not only observe the CMEs from multiple viewpoints, you can also reconstruct or try to reconstruct the CME 3D morphology and the geometry based on some method. That would be very helpful to study the CME interaction type and the CME 3D spatial overlap if we know their morphology and the geometry. And a wider method used in space science study is the graduated cylindrical shell model. It can just assume the CME has a flexible structure and try to construct it and make the reconstruction match with observations. So so with this information, we do research around the twin CME SEP ridge event in solar cycle 24. We have found 41 large SEP events at one point, and then we just try to mimic an identification by single viewpoint observation and by multiple viewpoint observations. So here is the result that would be quite clear. 2D means that we just do the identification from Soho Lasco from only single viewpoint observations. And the 3D means that we combine stereo A, stereo B, and we combine the GCS model. And the NP means that the event is not in the twin CME scenario, and the P means that the event is in the twin CME scenario. So the result is quite clear that when you have only single viewpoint observation, as for these large SEP events, you could identify that the twin CME scenario accounts for around 50% for the whole large SEP event, and this 50% is quite similar to the previous statistics in solar cycle 23. But when you have two more viewpoints, you found the percentage decreased to only 27. So the first answer is that the multiple viewpoint observation do affect the SEP detection significantly. And then we go to our second and third question about the CME interaction and its association with SEP acceleration and the release. So let me show you this figure. As for the let's see this part at first. As for the SEP acceleration issue, some people thought that you can use the observation of a type 2 radial burst to indicate the acceleration of the SEPs, because type 2 radial burst is a diagnosis of the CME-driven shock in the corona and through the interplanetary space. And so when you get type 2 radial onset time, you can just assume that the particles has been started to be accelerated. And as for the particle release, there are also many methods or techniques. The widely used one is the velocity dispersion analysis. This can be used to estimate the particle release time and the path length when the particle transport from the sun to the observer. So what is the velocity dispersion? So it means that if you assume all the particles at different energies, they are released at the same time or simultaneous, and they transport along the same path length, then the particles at higher energies should arrive at the observer earlier compared to the particles at lower energies because of the speed. So with this velocity dispersion, you do a linear fit, and then you can get its release time, and you can get its path length. And then we studied the CME interaction just basically based on the GCS model. And this tool is for the preceding CME information of its front and its tail. And this is for the primary CME. So you can see how the two CMEs will interact with each other when they propagate outward. And then we plot the type 2 radial burst time here and the SEP release time here. So that we can use to know how the interaction would be in association with the SEP acceleration and the release. And
is that coronagraph data?
Sorry?
Is that coronagraph data there?
You mean this one?
Yeah.
Yes, based on the GCS model. So it's like the CME 3D interaction. Yeah. So this is only for one case. We have 11 SEP rich or SEP large events in cycle 24. So you do a quite similar statistics. So this is a result. You don't need to just remember, you don't need to go to the details, but just remember that in this figure, the left white part means there's no semi-semi interaction. And in the middle gray and the right white part, it means that the semi-semi interaction is meaningful. So you can see some data points applies here. It means that it means that a meaningful semi interaction is not necessary for the SEP release, because the diamond means the SEP release time. And this left end means the SEP acceleration time indicated by the type 2 radial burst. And the y-axis or the y-axis shows the SEP peak intensity. And with these limited samples, it looks like that. Like we compare this part and this part, and this part. It seems that with these limited samples, when there is meaningful semi-semi interaction, it do lead to a higher SEP peak intensity compared to this part with no semi-semi interaction. So yeah, so that this answers our second and third questions. So let's go to a brief summary here. We have known the twin semi scenario is important, is quite important in the SEP acceleration and the SEP intensity. And we studied some questions about the twin semi scenario in solar cycle 24, and then we studied the acceleration and the release of SEPs associated with different types of semi-semi interaction. And we proposed something which related to the interactions. And I would like to skip this, and we go to our second story. The second story is still related to the twin semi scenario, but from a different viewpoint. So here, I'd like to recommend that for science or for scientific studies, we can always think about the questions oppositely. So this means that, for example, let me show you two cases. This means that we say that SEPs are generated by fast and wide semis. So is it possible that those fast and wide semis cannot generate strong SEPs? And whether the strong SEP event can be generated by slow and narrow semis? So that these are two questions. And as for our twin semi scenario, we know that the twin semi scenario will lead to an even more efficient particle acceleration. So it would be quite interesting to know whether there exists twin semi events, but not associated with large SEP event, even though the primary semi is fast and wide enough. So that we need to answer, and it would be interesting to do such a study. And to do so, it's quite easy that we just search for the events in solar cycle 24 or Y cycle 24 because multiple viewpoint observations again. So we found in total 19 twin semi SEP Pro events during 2007 and 2014. And here we combine this in situ spacecraft from stereo A, stereo B, and L1 point. Yeah, at L1 point. And we also as for the following studies, we also combined 11 twin semi SEP, the previous 11 twin semi SEP rich events together to study how to answer these different SEP detections associated with the same properties and with other factors. And here we limit our energy range in 15 to 40 MeV. This time, yeah. So let me show you the first result that we are trying. How can we use multiple viewpoints observation for the SEP detection in situ? This is the spatial distribution of the SEP peak intensity associated with the latitude and the connection angle. The connection angle means the magnetic footprint of the spacecraft relative to the SEP source region. So what is the meaning of the magnetic footprint? It means that you know that the charged particles will propagate along the magnetic field lines when propagate outward. And then in the heliosphere, the magnetic field lines is a spiral. So at a specific spacecraft, when you trace the field lines backward using the spiral, then you will get the foot points of one spacecraft. And you know the SEP source region, like from the flare region or active region, you could know this connection angle between each other. And the result here is that it only shows the SEP peak intensity at one spacecraft with the best magnetic connectivity. And it does show that the consideration of multiple in situ spacecraft would affect the detection of the SEPs, because you could see like the twin CME SEP pro events from the number decreases from 19 to 13. This is threshold in this energy range. But this is not enough, because we still have 13 twin CME SEP pro events. So what could we do more? This is only for, in this figure, this is only for observations, and this at some points the connection angle is not the best one. So we do a longitudinal distribution analysis for the SEP peak intensity at assumed point with the best connectivity. The best means that the connection angle equals 0. And the distribution profiles are shown here. You could see for most of the events, the observation and the fitting are above this threshold, But for some events, the observations are below this threshold, but the fitting shows the peak intensity are above this threshold. So with these two images or figures together, we know that first, magnetic connectivity between the observer and the SEP source region plays an important role in this SEP detection. So this is our first point. And then we go to the following point, is that we know like the SEP-CME relationship, and maybe we could expect to see the populations roll, the flares roll. So what can we do then? This is quite simple. It's that we study the one-on-one correlation between different factors, including between different factors and the SEP peak. And these different factors, including the CME speed, the flares, and the populations, but observed only near 1 AU, and the CME interaction information. And you can see some correlation coefficient here. The major point here in this page is that the CME speed plays as the most important role in the SEP peak intensity, because it seems that it has the highest correlation coefficient between these two factors. But for the remaining one, like the flare, the seed populations, or something like the CME interaction, it looks like the correlations are not such weak. With, for example, with CC between 0.3, 0.4 and 0.5. However, there exist some problems here when talking about like the flares or seed population, or even the CMEs. Talking about these one-on-one correlations, let me show you why there exists some problems. The first reason is that there exists some intrinsic relationship between these parameters. For example, the CME and the flare, we have known the CME and the flare are closely coupled with each other. So when you have a fast CME or when you have a strong flare, sometimes you could expect a fast CME. So this intrinsic relationship will first influence the one-on-one correlation. And the second is that we don't know the exact expression, or we don't know the exact physical mechanisms in the SEP production or in the SEP acceleration. So we don't know how to express how they will contribute to the SEP peak intensity. So how can we do, like, even we have these two questions, how can we combine all the things together to think about the SEPs and all the independent factors? Okay, luckily we found one method This is called the projection correlation analysis method. It has two advantages which are very suitable to our motivations. One is that it is suitable. It can combine multiple independent and dependent variables. It means that we can put all the factors together to study such a correlation. And the second is that it doesn't require specific tuning parameters and the moment conditions on the variables. So it means that even though we don't know anything about the expressions of the, like, for example, the semi-semi interaction and an SEP, we can also get an correlation coefficient. And the results of the different combinations of our independent factors are shown here. It has like only the semi-primary speed, the primary semi-speed, and the different combinations like the flare, the particle populations, and the preceding semi, and all the factors together. The correlations here. So we can see something based on this figure. The first is that the projection correlation method also shows that the driver semi or the primary semi speed is the major factor in controlling the SEP peak intensity. And with these data points, it looks like a combination of the latitude of the CME propagation direction here, here would increase, but although slightly, the related projection coefficient. And then why the latitude is important? Because latitude can act also like a kind of magnetic connection, but it's in latitude. And then the third is that other combinations of other factors does increase the related projection coefficient. So that is quite surprising to me. So it means that when you consider flares, or you consider seed particle populations, it seems that they won't contribute to a bad SEP prediction. So, and with all the information together, let's make a brief summary here. We start from the twin semi SEP Pro event, and we found that the magnetic connectivity and the primary semi speed would be the major two factors influencing the SEP in situ detection. But we found that a combination of other factors, for example, the flare size, the seed populations, won't improve the prediction of the SEP peak intensity. And let's see the SEP populations level here. This is what the SEP population in these studies, we use only for we only use the 1 AU observations. So it means that these seeds are quite far away from its acceleration region. So whether there would be something happen when between such a 1 AU or even more than 1 AU distance, that we would like to know, and this will lead to our third study. The third study, okay, we're finally talking about the seed particle populations in the heliosphere. So let me briefly introduce the importance of the seed particle populations. So it's important in the SEP shock, in SEP acceleration mechanism, like this diffusive shock acceleration, and it acts like an injection to the shock where the acceleration acts. And as for the origins of these seed particle populations, people are thinking that they are the lower energy portion of the materials accelerated in energetic particle events associated with, for example, with qualitative interaction regions, with the semi-driven shocks. This is related to our previous twin semi scenario, and associated with solar flares and even the continuous acceleration processes in interplanetary space. And the energy range of these seed particles can range from super thermal, like some people think from super thermal, and some people think from 1 to 2 MeV, and even some people think this energy range can be up to 10 MeV. And in this third story, we focus on this 1 to 2 MeV region specifically. And so let's recall our question again, because some previous studies try to link the seed particle populations in the corona with the 1AU observations, and they try to say, okay, we observe the same thing, and the observations near 1AU can represent those seeds in the corona. But our results and one previous paper by Kaler, they showed that the seed particle population observed near 1AU in the SEP peak intensity prediction, there may be some problems. So with these things, with these questions, we can always ask questions. And for this study, we asked 3. Like the first is that how long the seed particle population can exist. So this means, for example, when you drive for example, in a twin semi scenario, when your preceding semi erupts and you have a weak shock, you produce those seed particle population, and how long they can exist there to be caught up by the following semi, by the primary semi. So this is the first question. The second question is that how widely these seed particle populations can extend or spread in the heliosphere. And the third question is related to these statistics. How seed particle populations measured near 1AU correspond to those in the inner heliosphere, because we know that the acceleration always occurs near the in the corona or near the sun. So to answer these 3 questions, of course, we need observations in the heliosphere or close to the sun. And then luckily, we have like Parker solar probe, we have solar orbiter. And for this study, we focus on a series of SEP events observed by Parker solar probe and STERO-A in 2020. And during this time, you can see Parker solar probe was at around 0.3 AU. And these 4 SEP events are generally from these 2 major source regions, and these 2 arrows shows the longitude of these 2 source regions. And the magnificent points are estimated, and the angular separation between the spacecraft magnificent points and the SEP source regions are shown here. So you can see with this image, first, the PSP was quite distant from STERO-A with an angular separation of around 100 degrees. And then the second, the foot points of these 2 spacecraft are quite distant from the, okay, thanks. Quite distant from the SEP source region. So that will lead to some interesting results later. Let's see the in situ counterpart. This is the in situ SEP observations by Parker solar probe and by STERO-A at different distances. And they showed observations in different view angles and at different energy ranges from, like we focused on the 1 to 2 MeV, and here, though a little bit higher, but still close to 2 MeV. And the different viewing angles means that you have, like for the telescope, you have 2 viewing angles. One is quite roughly along the Parker spiral toward the sun, that you are facing the sun, and the one is outward, so that you are anti-parallel to the sun. So with this information, you can see some properties between observations at PSP and at STERO-A. The one is that its magnitude. The magnitude of the proton enhancement at PSP is much higher compared to those at STERO-A by a magnitude of 2 to 3 orders. And then secondly, you might notice that the proton intensity enhancement for the first 3 events, they show a quite low anisotropies at these 2 spacecraft. This low anisotropy means that the proton intensity observed along different view angles have a quite similar magnitude. So you have two information, and now this is only for the in situ counterparts. We need to do for the remote counterparts for its drivers, for the SEP drivers. We identified that there are 8 semis associated with these 4 SEP series, with these 4 SEP events. And then let me show you one more page about these drivers. We do the identification based on the radio burst observations, based on the UV observation to identify the filaments, and based on the white light chronographs. And we found 8 semis. And the semi parameters are listed here. 2 things need to two things to be noted. The first step is that if we look at the angular width and the speed, except the first one, the first semi, the following one, the semi speed and the angular width are not such large, with angular width smaller than 60 degrees and with the speed smaller than 500 kilometers per second. And then the second is that for the third SEP event here, there are three successive semis erupted in a short time interval. So this would lead to the SEP properties between each other different. So so we now recall our first question, that's how long those seed particles can exist when they are produced. To do so, it's quite simple. We just study the decay phase of the SEP event. The decay phase is of interest because it could indicate the formation of energetic particle reservoirs in the heliosphere. And we do an exponential fit to the decay phase of each event. And this is, we got a decay time constant here. And then we also, this is based on observations, we also do a theoretical estimation by considering the dominant role of convection and adiabatic deceleration in the solar wind of those SEPs. And then we could also estimate a decay time constant. So we focus on these three events, these first three events, because they are from the census regions. And the decay time constant is around 10 to 20 hours. That answered our first question, how long? And then we now focus on the third SEP event here. The decay time constant estimated in observation are quite larger compared to the preceding one, and quite large compared to the theoretical estimation. Then it may indicate the three successive semi-injection would cause such a longer decay time constant. And then we go to our second question, how widely? This could be easily answered by the distribution of the two spacecraft. Maybe it is quite wide with angular separation of around 100 or even above 100 degrees. And for the third question, what's the difference between the observations in the heliosphere and the near 1AU? The 1 point here is the magnitude by an order of 2 to 3. So that would together answer our second and third questions. But let me show you one more figure or one more discussion about the differences between the observations in the heliosphere and the near 1AU. This focus on the decay time at PSP, the blue one, and at still A. For the third SEP event, you could see for this event, the decay time at still A is much longer than that at PSP, when still is here, PSP is here. And in the absence of broad particle sources and the narrow CME and the quite large angular separation between the SEP source and the magnified point, we can think that the transport of the accelerated particles from the acceleration region to the spacecraft is caused by the cross-field diffusion. So it means that the particles would be transported perpendicular to the magnetic field lines to the spacecraft, or to the field, to the spacecraft. And as for this, as in this figure, as still A is quite far away from PSP. So if you assume a CME is propagating outside along this direction, it will continuously accelerate or generate particles. And these particles would be continuous transport to still A because it is quite far away from compared to PSP. And this is one reason, the continuous injection by one CME is when it propagates outward. And another reason is that you just consider the rotation of the sun. It will rotate from east to the west. And all the particles filled in this region and the field lines with accelerated particles will be rotated to connect still A when the sun is rotating. So these two factors together may try to answer why we have a longer decay time at still A. So we have compared the magnitude, we have compared decay time between the inner helisphere observations and the YA observations, and we could make a summary like this. This is a quite simple summary. And one thing I would like to emphasize is that we try to propose a scenario as for the generation of seed particle populations. This is that the seed particles can be continuously generated by eruptions associated with emphasize slow and narrow CMEs, because as for this event, for this series of events, the CMEs are not quite fast and wide. And they can spread over a large part in the inner helisphere, and they can remain there for tens of hours. And even though the minimal particle intensity enhancements are measured near YAO, so that is based on when compare the still and PSP observations. So this is the third story. And then now, before we go to the final story, the role of the seed particle populations and here, and the final one is not related to the seed particle populations, and the final one is just like a bonus, that how can we use the current or the advanced observation from multiple viewpoints and then multiple wavelengths to study the SEP and associated phenomena. So let's have the final one. The final one is related to the SEP release and the coronal UV wave. We know that coronal UV wave, though its mechanism has been largely debated, but it was thought to be the foot point of the coronal shock on the solar surface. So you know that shock accelerated SEP, accelerated particles. So you might try to expect there may be some relationship between the UV waves and the particle acceleration. And some people try to answer that when the particle or the SEP is released, are released when the UV wave connects to the spacecraft magnetic point, and especially for widely spread SEP events, and they try to link the UV wave with the SEP release. But whether this is true, is this true or not? Davis or Larry's studies answer no, this is not true. There may be no relationship between UV wave and the SEP release. Why? They show some cases. Those cases show that you observe the in situ SEP enhancement, but you don't observe the UV wave connecting to the foot point. So these provide an opposite condition that there's totally no relationship between these two phenomena. And this is for David's or for Larry's study. It's only considered the things without connection. But can we ask that whether we could have some events that the UV wave connects to the magnetic spacecraft foot point, but you could also observe a delay or an earlier SEP release. So we found one last year. So this one is based on a study using multiple viewpoints observation and in multiple wavelengths. We have 4 spacecraft now. We have COA, we have PSP, we have solar orbiter, and then we have spacecraft at one point. One advantage for this event or for today's observations is that we can have not only the longitudinal separation, we can also have the distance separation for spacecraft located at different distances, but along a similar magnetic field lines outside. So that could be used to test the longitudinal effects and the transport effects when the particles propagate outside. So this is the spacecraft location. And for this event, of course, we observed the UV waves associated with the same eruptions in UV wavelengths and in white light coronagraphs. And this is not, we could observe this foot point of the spacecraft and how the UV wave pass through this foot point here. And then as for the in situ counterpart, let me show you one more. As for the in situ counterpart, we observed the SEP enhancement, like proton enhancement at all the four locations. at solar orbiter, PSP, and still and L1 point, and in different energy ranges. And with these in situ observations, we estimate the particle release time based on some method. Not only the VDA is used, but also the time shifting analysis method is used for particles at quite higher energy ranges. And the one release time results are shown here. And you don't need to remember the detail of the particle release time, because I will show you one more image here. This is what we try to find in this event, is that this is the time when the UV wave connects to the magnetic point. And the vertical line, these 4 vertical lines, is the particle release time based on some estimations. And you can see that even though for this event, we have 4 spacecraft, but for this 4 spacecraft, we could observe a delayed particle release time after by 20 to 40 minutes after the UV wave connect or pass through the magnetic point. So this may bring us one more evidence that there's no relationship between UV wave and the SP release. And one more bonus in this study and our future study is that we have multiple viewpoints in multiple wavelengths. We can do some models. We can try to estimate the shock properties and try to answer many things like related to the particle acceleration and the particle release together. So let me skip this summary. And we have our final page. It is quite simple. This page means that this only based on my personal understanding that as for SEP study, or not only SEP, but also CME studies, we have observations, we have theories, we have simulations. How can we combine them together to have a better understanding about our science is important in the future. And this is like a triangle, but they are equivalently important. Why I put this observation on top is that I am talking about observation today. So thanks a lot. That let me end my talk here.
Great, thanks, Ben. Do we have any questions firstly in the room? Yes, Tony.
Hi.
Hi.
I don't do SEP events, but my questions are going to be somewhat basic. Those are sometimes the hardest ones, but okay. Back in the day, we used to see a classification scheme for SEP for gradual versus impulsive, where the graduals were particles that are accelerated by the shocks preceding CMEs and tend to be broad energies, whatever. Impulsive would have to be more from the flare directly towards source particles. But some of these might be seen differently depending upon your longitude in space.
Yes.
As to whether you might classify as impulsive, narrow, higher energy versus gradual. My impression here is, well, first of all, do they still use that classification or has something evolved? It looks to me like what you're doing here, because you look at CME shocks, is what we used to call gradual.
I think there's an update in 2019 or 2020 by RIMS. He updated the terminology into 4. So like,
that doesn't help me go from 2 to 4.
yeah, but the things, but basically to me, it just I don't know, this is, I should mute myself that from the Zoom part. To me that I don't exactly care about how to define those things. If you go to the further physics inside, then what we need to do is only how they are accelerated.
Well, I'm going to suggest that, I mean, you're using as one of your parameters to look at something about flares. I'm not sure what about the flare, but something about a flare.
Yeah.
You could have a CME without a flare.
Yes, true.
Okay.
Yes.
So therefore, it would seem to me that one classification for looking at data would be what are simply CMEs and what are CMEs that were associated with a flare.
Yeah, some events are quite a hybrid event, means that there is a combination of the impulsive one and the gradual one. So it means in that single event, both factors could contribute together.
I agree, but
Yeah.
there are CMEs where there was never a flare, just to be clear.
Yeah, true. Yeah, yeah,
So
I know,
to me,
also
if
some
if you're
CME.
going to use flares as one of your parameters you're looking
Yeah.
at, you may want to further subdivide those events that are CME only
Yes, true.
versus CME with a flare.
Yes, true.
Okay. Another question I had, I think that the view angles of the instrument can be very important if you're going to be taking a look at solar probe versus stereo.
Yeah,
And I'm not really clear what the view angles are when you're taking a look at this. I assume that solar probe might have a broader one since the Parker spiral changes over radial distance.
Yeah.
But I do know that the stereo A, have you taken into account that the
yes,
energetic Parker instruments were pointed toward the Parker spiral that was
Yes.
launched?
yes,
But then the spacecraft flipped when we went into solar conjunction, and so therefore it is no longer
yeah,
pointing at Parker spiral. Therefore, if one instrument is looking toward the Parker spiral and the other is not, how do you compensate for the fact that you have totally different viewing directions? And then, say that one has a higher intensity than the other.
yeah,
It seems to me that would have to be investigated to show that it's not simply where you're viewing, that it's impacting what's going on. So I don't know if you've done that, but just remember that the stereo spacecraft flipped to a
Yes,
solar
sure,
conjunction.
yes.
Therefore, it's no longer pointing
yeah,
at the Parker spiral, the nominal Parker spiral.
yes,
The other thing, of course, is that when you're looking at source regions, you mentioned CIRs. CIRs, of course, are fully developed between 1 and 2 AU, not the inner
yes,
heliosphere,
yeah,
and therefore the particles stream back along the
Yes.
lines,
yeah,
back toward the sun rather than away from the sun. So I think looking at where you are in the solar cycle can be
Can you follow?
important to determine whether or not
Yeah.
CIRs, I mean, because you can also find your CIRs. They're listed, but
Yeah.
To take a look. The other thing, and this is something I've never totally understood, so let me just bring it out here.
Yeah.
These are supposed to be the shock accelerated particles from the CME. The CME does not go along the Parker spiral. The CME comes out as almost radial.
Yeah.
And its shock is pretty much coming out radial.
yes,
So it's not clear to me why you would look for the footprint based upon the Parker spiral where it hits on the sun, rather than where you might magnetically connect somewhere in the inner heliosphere to a radially
Yeah.
propagating shock.
yeah, to the nose of the shock, yes, to the nose of the shock.
Yes.
I
So,
never understood why you keep going with the Parker spiral back to the sun.
no, it means,
Well, you go to the park, you go to the spiral, but you find out where that spiral, connects with the shock.
yes.
Yeah, but he was doing the coronal ray.
For the coronal wave, for the UV wave is that,
Oh, that's.
yeah, the previous studies, you can, if,
I mean, I can understand if you're doing the impulsive flares, what we used to call
Right.
those.
yeah,
But with the gradual ones,
Yeah, for the coronal
One
wave.
of that back to the shock those.
yeah, that's because some studies try to link the UV wave with the particle release, and the UV wave is on the solar surface.
But that's a particle release with what we used to call the impulsive flare,
No,
because the particle release for the gradual ones are created from the shock that's coming.
yeah, but the UV wave, they can act like the footprint of the shock of the coronal shock driven by the CME. So this is still quite related to the CME driven shock, even though you can have flares there, and then you can have a CME driven shock, and that shock propagates outside, and its footprint like a shock, it has foot on the solar surface. That some people thought that foot formed the UV waves.
I know what the EV
Yeah.
waves are, I'm just not sure why a shock created particle thing that's being created within the inner heliosphere as a shock is getting stronger. But which the density is getting lower, that's what would then be related to.
Yeah.
So I'm not frankly, totally surprised if they don't match up, but if they do, we want to look to see if we have it also later.
Mhm.
The other thing was, and this again is terminology, you need to understand the difference between a valve shock for a CME versus a piston driven shock for a CME.
Yeah, I tried to understand this, but I have my own understanding, but I don't know whether this is
Well, I've never heard valve shock used for a CME.
no, it's most
The project assumes that, you're stationary in some airplane, like the Earth is.
most
The piston driven
piston
shock is
driven
the
shock.
same thing. I mean, it's an impenetrable barrier, but it's moving. Okay, and so it's a now it's a traveling shock rather than a stationary one, like the bow shock.
Yes.
Yeah, but this was referring to CME shocks.
Yeah. It's just, the CME is basically an impenetrable barrier that's propagating outwards, and so the shock that's produced by that object, okay, is a traveling shock.
But that part I understand. So maybe I just misunderstood the view graph. Because I thought you were saying that CMEs could have a valve shock.
Maybe I didn't mention the
A moving bow shock.
yeah. Okay.
Right. I
Yeah.
think
You
So
go
again,
go ahead.
no, you had
Let me
something else to say on
very
that.
quick answer. The question about the stereo flip, and as for that PSP stereo event, quite lucky that we don't have stereo A flip during that time.
Pardon?
Quite lucky is that we don't have stereo A flip during that time. So I have checked all the viewing angles of stereo A and the PSP. And one more lucky thing is that the particles are quite low anisotropies. So that means that the viewing angles may even though it's changed, but it won't influence these low anisotropy results a lot.
But LAT is not that low. It's not super thermal range. It's higher.
Yeah, that is not such low. That's true. But at PSP, we are unlucky to have IP low data during that time, so that we could only do for the.
No, I understand that, but
Yes.
you have to, if you're going to say the intensity is higher here and lower here, you
Yeah.
have to address the issue of where are the two instruments looking? And
Yes.
therefore, could they be looking?
Yes. Yes.
Could a reduction in the intensity? I mean, I'm not saying that you're
Yeah.
wrong. I'm just
Yeah,
saying
yeah,
you
that's-
have to
that's the
address
best.
that.
Yes.
It could, especially that you're looking
Yeah.
behind you instead of.
Yeah. That's a very good suggestion. Yes, true. Yeah, lucky.
So I understand your twin CME scenario here. I mean, I've always thought of the first CME as the one that's producing the seed particles
Yeah,
for the trailing CME.
yeah, for the following one. Yes,
Okay.
yes, yeah,
Okay, so when you look at the seed particles. Okay, I mean, you're basically looking at that line between the two shocks. Is that what you're doing? Playing those are the seed particles?
yeah. Just you. When the preceding one erupts, then you will,
Okay.
yeah. That exactly what you are saying.
But
yes.
is the shock speed of the second CME?
Right.
within the first one? You know, great one.
Yeah, it does require that the second CME should be fast or very fast, significantly faster than the preceding one, but it requires a specific time interval between these two CMEs because this is related to one question: how long those seeds can exist or can be there to be catch up by the second CME.
Right, but you look at the decay time of the SEPs to try to ascertain that. Okay. But have you looked at the turbulence data?
Not exactly.
Okay,
No.
okay,
Yeah.
to get an order of magnitude
Yeah, that's
of the diffusion coefficient, and that would see if that jives with.
Yeah.
The decay time, whether it's it's, diffusive.
Yes, that would,
Diffusive transport or something else.
yeah, that would be interesting to know in the future. But currently we try to move a step further to see how can we use those things to initiate our studies.
Yeah.
Yeah.
It's not a wavelength field, I think. No.
Cool. Great, I think we have one question online from Carlos. So I guess we'll have to mute ourselves in the room.
Hi, can you hear me? Okay, nice presentation, Bing. My question is about the relation between the perpendicular and parallel diffusion that you commented in the second part of your presentation. Do you have an idea how is this relation? How big is the difference between the parallel and perpendicular diffusion, and how much do you need to make your point about the gradual decrease in stereo compared to Parker's solar probe?
You mean my second part is the comparison between Stereo A and Parker, or the twin CME SEP Pro part?
Yes, I think that one, yeah. You have one very high, very steep decrease and one very gradual decrease.
Yeah, I see. That's I know what you mentioned. To be honest, I don't know exactly the portion of the perpendicular diffusion to the like the parallel diffusion. For example, we talk about the coefficient because we didn't estimate such a coefficient. But one thing that with the angular separation between the source region and the two spacecraft, and with the low anisotropies and with the narrow driver CMEs, we might expect a quite stronger cause field perpendicular diffusions, because you need cause field diffusion to transport those particles to the field lines connecting to the spacecraft. But for the exact values, I can't answer now. Sorry about it.
Okay, I'm just curious about it. But thank you.
Great, well, thank you. And I think we're over time now. So thanks to Ben again. And thank you for everyone that joined us in person and online. Thanks, we'll see you next time.